the second part of my Circle Theorems Explained series, where we look at the proofs behind all your favourite theorems. If you haven't watched part 1, I highly recommend it, as although you'll understand this video without it, we'll use principles from it to prove this theorem. The theorem being, opposite angles in a cyclic quadrilateral sum to 180 degrees. We will also use this theorem to prove that angles in a semicircle are 90 degrees. Let's start with the basics that you'll need to know. Firstly, a cyclic quadrilateral is a four-sided shape where all four corners touch the circumference. For example, the shape in this circle here. We'll come back to this. You'll also need to know the theorem of the angle at the centre of a circle is double the angle at the circumference. Again, if you do not, you should watch my previous video where it's covered in detail. Leading on from this, you should know that not only does the theorem appear like it does here, but it also appears like this. We return to our cyclic quadrilateral. We're going to label this here angle x. Now, we draw two lines connecting the two adjacent corners to the angle to the centre of the circle. You may recognise this shape from what we looked at earlier. The other way, that the angle at the centre being double the angle at the circumference, can be applied. We can therefore label this here angle to x. However, this is not the angle we need. We need this angle, labelled in green. This angle is conjugate to the one that we have, as it is around the same point, and angles around the same point sum to 360 degrees. Therefore, our next angle is 360 minus 2x. We now focus on the angle opposite our initial x. What do we notice about the relationship between this angle and the angle that we just calculated? Once more, we return to the theory of the angles at the centre being double the angle at the circumference, to see that this unknown angle will be half of 360 minus 2x. 360 minus 2x over 2 will give us 180 minus x, our value for the angle opposite x. Time to test our theorem. X plus the angle opposite, 180 minus x, does in fact get us 180 degrees, so it's correct. This line of proof will work with any pair of angles that we try it with. For example, if we try it again with the other pair of angles, it will still be correct. We label this angle y. This angle is double y by the angle at the centre theorem, and this angle will then be equal to 360 minus 2y. Halve it to get the angle opposite and you'll get 180 minus y. Add y and you'll get 180. Once again, proving our theorem. This represents a right-angled triangle with its hypotenuse as the diameter of the circle. The right angle is shown by the square at the angle. Notice that if we add another angle on the other side of the diameter, no matter where it is, it will form a cyclic quadrilateral. The angle will also always be opposite to the right angle, which is 90 degrees. So, in order for the angle to conform to our theorem, it must always be 180 minus 90, or 90 degrees. Please note that while this does work, it's not the most commonly accepted proof, as it does not prove that the first triangle is a right angle. For the correct proof, you can watch my next video on why angles in a semicircle equal 90 degrees. Thank you for watching, and do consider liking and subscribing on your way out. Until next time, mathematicians.